Welcome to lecture 12 of Mathematical Modeling and Simulation. In this lecture, we are going to look at traffic flow model, which is one of the interesting models studied in literature, and most of the researchers all over the world are working in many areas related to traffic flow modeling. So basically, we need to understand what is this traffic flow model all about. And to understand that, so without any delay, let's start. So firstly, I'll be explaining you what is traffic flow and then why we study it, what are the objectives of traffic flow modeling, and then what are the general assumptions involved in the modeling part. Further, we'll discuss various classes of traffic flow models. If you remember in our previous lecture, we have talked about the general classification of mathematical models, but right now here we'll be specifically talking about classification of traffic flow models. And then we will pick up one model, which is macroscopic traffic flow model, and we'll have its basic introduction, define the fundamental variables, and we'll also derive the relationship between fundamental variables. So let's begin. What is traffic flow? So what is the first thing which comes to your mind when you listen or read the word traffic? So obviously, if I'm not wrong, most of the people's mind work that way, that we often imagine there's a jam kind of situation, there's a traffic jam, or the vehicles moving over highways. They can be in cities or towns also, but basically traffic flow is nothing but the flow of vehicles. The traffic is a very general word if you understand. It's also used for network traffic, like our internet service providers. So the network traffic is heavy, or it's also used for the traffic inside our cells, that the molecules or the proteins are moving inside our cells. So there also a jam kind of situation, there also a congestion can be there. So traffic is a general word, but most of the times we use it specifically for vehicular traffic, the traffic which comes to our imagination whenever we hear the word that the vehicles are moving on the highways. So specific word is vehicular traffic, but let's just call it traffic flow. So as such, there is no formal definition, but it's just about what is traffic flow. So now we need to have some motivation of studying this, that why we are studying this. So we know that why this world is constantly modeling traffic flow, because in a constant effort of reducing traffic congestion in today's overcrowded world, this field is gaining popularity, and all over the world mathematicians, physicists, engineers, economists, and even practitioners of operations research, so they are working for designing efficient traffic flow models so that we can overcome congestion. So here you can see a video of 2015 in which a 10-kilometer long traffic jam was witnessed on Beijing Hong Kong Macau Express Highway. The exact reason of this jam is not known so far, but it's believed that it was during that you can say the New Year time, people were going towards their native places, so they were traveling all the way on this highway. So there were so much people traveling at the same time that it resulted into a long traffic jam. It lasted for 3 to 4 days. And the statistics also tells us only in the USA, largest urban area, an average traveler wastes 62 hours per year just because of traffic jam. So that's the situation in a developed country, you can imagine, where we can expect the infrastructure and everything else to be better, much better as compared to the developing countries like India. But there also you can see the amount of time wasted by traveler in traffic jam is quite high. And this is not only a wastage of time, this is a wastage of economy. This causes a huge loss to the economy as well. So there are many undesirable consequences of traffic congestions. They can be undesirable for an individual, and they can also be undesirable for economies and nations. So that's the motivation, or we want to study traffic flow modeling because we want to overcome with this situation. So this gives us certain list of objectives of traffic flow modeling. So we have these objectives. First objective is we want to optimize the flow. Like here I will not be using the word to maximize the flow, because see, when you're driving your vehicle, whatever vehicle you are driving, a two-wheeler or a four-wheeler, you know that there is a speedometer which tells you that this is the maximum speed of your vehicle. But it's very very rare, and in fact it's almost rare that we never drive at that maximum speed. We drive at some optimal speed like 80, 100, 60, or whatever be the optimal, depending on your road conditions, depending upon where you are traveling on highway or wherever. So we optimize our speed or the flow according to our situations. So that's why the word used here is not maximize, it's optimize, because it depends upon your other circumstances also. So vehicular traffic is studied because we want to optimize the flow. We just don't want everybody to rush at the maximum speed. We just want they should drive or they should be flowing smoothly so that no congestion occurs. To reduce traffic congestion, I've just told you. To help engineers decide planning of road or highway network. Yes, so this is also an important point here. This is the reason why engineers, the engineers who are working in this area, why they study traffic flow modeling, because they want to give a better and efficient planning of road networks or highway networks. And obviously we know that why that is required. To understand the reason of occurrence of traffic jams. Just now I gave you an example of a big traffic jam. So many researchers are still yet working on that, how that jam could have occurred or what could have been avoided. So people are trying to understand these reasons of occurrences of congestions. To develop intelligent transportation systems like driverless cars. So that's also an important area which is gaining much popularity in recent times, because you might be already familiar with the idea of driverless cars, that they are coming up very soon, and a lot of trials all over the world are going on. So they are part of intelligent transportation systems. So to understand them, obviously to develop these kind of systems, we need to understand various uh, you can say various perspectives of traffic flow needs to be understood through mathematical modeling. And last but not the least, to reduce traffic accidents. In fact, this is covered in the to optimize the flow, that we want to design the road networks like that there will be less number of accidents. So although from these objectives you might be anticipating or expecting that we might do something like that, but exactly we are not going to fulfill all the objectives through our modeling. We're just going to have a very basic introduction of how traffic is modeled. So now let's talk about few general assumptions which are followed for traffic flow modeling. So soon from the next slide I'll be telling you the classification of various traffic flow models. So there are more than one ways. There is more than one way in which we can model traffic flow, but for every kind of model there are some general assumptions. So those general assumptions are, the first one is drivers always obey traffic rules, and I don't need to tell you that this is a very unrealistic assumption, because we know that even if you consider the traffic in a small city, so we know that the percentage of drivers which are disobeying traffic rules in one way or the another is high. So that's why we can say these kind of drivers are most of the times responsible for causing local congestions, local traffic jams. For that jam can exist for 1 hour or 2 hour or even for a few minutes, but it's most of the times due to the insane driving behavior of some no disobeying drivers. So that's assumption, because in our model we cannot incorporate the driver's psychology. So the kind of models which we are going to model are going to work based on ideal driver condition, that okay, we assume that driver is going to obey all the traffic rules. So that's an assumption which comes with every model. Although there are specific models which talk about, okay, what if you include the factor of driver's psychology, driver's behavior into your model. There do exist models like that, but this is a general assumption. So we know that that's an irrelevant assumption. So drivers are driving like anything. They are disobeying traffic rules most of the times. And the next assumption we have is that each vehicle's length is same. We'll be studying different kind of models, but in most of the models, this is the assumption that we assume that each vehicle's length is same, because you will see that the aim of traffic flow modeling is not going to be tracking just one vehicle, that how that particular car is driving or how that particular truck is driving or moving. We want to understand the general behavior, that if this is happening on road at this hour, will there be a traffic jam in the evening or not. So we are not specifically focusing on one vehicle. So that's an assumption. We assume every vehicle is of similar length. We ignore the individual characteristics of the vehicle, right? And each vehicle is called a car. So that's another assumption. Just to simplify, we just don't want to call the vehicle is running, we just say the car is running. So car is a general word, so don't get confused, because we'll be very frequently using the word car. So that car does not mean the real car. It can be any vehicle. It can be a truck, it can be a another four-wheeler, so whatever it can be. So these are the general assumptions. And now specifically we are going to talk about classification of traffic flow models. So here are few classifications, although again I'll say the list is not complete. There are many other ways also, because as the area is developing, more and more researchers are working in this area, so they are individually identifying their own type of models they want to work on. But the most important ones are these: macroscopic, microscopic, mesoscopic, cellular automata, and stochastic models. So specifically here I'll say that we will not be able to discuss all of them because of our course content and time restrictions, but I'll give you a fairly good idea of most of them so that you develop an intuitive understanding of different kinds of models you need to work for traffic. So the most important one of them is and the most commonly used is the macroscopic. So in this today's lecture, I'm going to start with the macroscopic traffic flow model. So what is this macroscopic model? So this is something you can understand from the literal meaning of the word macro. Macro means something at a bigger scale. So the first assumption of this kind of model is it does not focus on individuality of each vehicle. So if you read this precise definition here, that if one looks into traffic flow from a very long distance, the flow of fairly heavy traffic appears like a stream of a fluid. So you just imagine yourself, you are on the top of a hill and you're looking at the vehicles or the cars moving downhill there from a very, very large height. Then you may imagine them as a fluid flowing, because if the number of vehicles is large, the number of cars is large, it may seem to you that some liquid, water or some fluid is flowing. So that's the basic assumption, or you can say that's the analogy on which the macroscopic traffic flow model works. So a macroscopic theory of traffic can be developed with the help of hydrodynamic theory of fluids by considering traffic as an effectively one-dimensional compressible fluid. So the fluid mechanics, the fluid is having its own theories, because when the fluid is flowing, it's giving rise to a mathematical model. So there is a whole lot of theory dedicated to the fluid mechanics or fluid dynamics. So the macroscopic model is assuming that we can use the similar concept or similar, you can say, analogous interpretations as we use in the hydrodynamic theory of fluids. So the macroscopic theory, basic assumption is this, that here the traffic looks like a stream of a fluid. So now you just imagine that whenever you look at the water flowing, so you're not able to see the individual molecule. Although we know that the motion of the water flowing is being carried out by a set of collectively large number of molecules, but you're not interested in looking at their individual tracking of molecules. All what we are interested in, what is the speed of water, or with what velocity it is flowing, with what is the flow rate. So that's the average things you are going to talk about. So that's the same thing we are going to do in this traffic flow model. We'll not be interested in individual behavior of one vehicle at a time. Rather, we'll be interested, okay, as an average, what is the flow rate or other things. So this also comes with some additional assumptions. So the first assumption is the traffic flow is conserved, or in other words, vehicles are not created or destroyed. So this is the same thing which we talked about in our previous lectures when we discussed about conservation laws, that using the law of conservation of mass, energy, momentum, we can build mathematical equations to understand any real world phenomena. So that's why. So here also we will try to construct a model based upon the conservation law. Now, which conservation law is going to be used here? Law of conservation of mass. So that mass is nothing but an individual vehicle. That assumes that no vehicle is created or destroyed by itself. So we'll talk about the conservation law in detail later, but right now here I just need to tell you this is an assumption, and that's a valid assumption because we know that that's applicable here. And the second assumption says there's one-to-one relationship between speed and density as well as flow and density. So I'll come to this because the speed, density, flow, what are these? I'll talk about these in detail, but here we need to understand the meaning of one-to-one relationship. So one-to-one relationship means for one value, like if I'll say there are two variables x and x and y are having one-to-one relationship, that means for each value of x there is exactly one value of y. It's not a multi-valued kind of function. So anyways, let's talk about mathematics, and for that we need to define fundamental variables. So remember, now we are in the one category of model. This is not a general theory. Now we are specifically talking about the macroscopic traffic flow models. And for these kind of models, there are three fundamental variables: density, flow rate, and speed. So again, you can understand it this way, that in classical physics, whenever you want to describe the equation of a state or a gas or a fluid, all what you are interested in knowing the PV equals to nRT. That's the equation which we know that which connects the pressure, volume and the temperature. Because we are only interested in looking at what is the pressure, what is the volume and what is the temperature. They're not interested in looking at the molecular level of the gas. So in the macroscopic systems containing a large number of particles or vehicles, we are always interested in measuring few quantities, few observables or measurable. So these are those three quantities we'll be interested in measuring: density, flow rate and speed. Obviously these will be average. They'll not be the related to one particular vehicle. So I'll come to these one by one. Density. Usually we know the definition of density from physics is mass per unit volume, but here I am going to give you the definition of density in the context of traffic flow, and again we are working right now in one dimension. Like all the definitions which I give you are assuming that all the vehicles are moving back to back, like there is no overtaking allowed. This is just a one-dimensional model. The vehicles can follow other vehicles but they cannot overtake, because overtaking requires moving to a other dimension. So it's just a one-dimensional flow in a queue kind of flow. So for that this definition is applicable. That's the number of cars. Again, car is a specific word. It can be the number of vehicles also. The number of cars per unit distance at a given time. So here is something we need to understand, that see, these three are our fundamental variables. So these are dependent or unknown variables. We want to know their values: density, flow rate and speed. And independent variables are going to be space and time. All of these are functions of space and time, because in one part of the road or at one side of the highway, vehicles are moving quite fast because there is no traffic jam, or you can say the less crowded highway it is, or while on some other highway or some side linking road there is a congestion because of an accident. So density, whether there is a number of vehicles is more or number of vehicles is less. So that's what we mean by density. So that is a function of space. It depends upon where you are, and it's also a function of time, because in the morning time when everybody is going to office, a particular, you can say, a particular part of the city can be crowded, it can be highly dense, but with the time, as the day passes, the traffic may reduce there, the density may reduce there. So this density is a function of both space and time. That's clear. Similarly, the other two variables, the flow rate as well as the speed, is also a function of space and time. So this density is the number of cars per unit distance at a given time. So when we are defining it, so we are fixing time here, but we are measuring the number of cars in a particular distance. Like we fix 2 points on the road, that between this much I have to count how many cars are there at this particular instant. So we have to, like, at exactly 4 p.m. in 1 kilometer stretch of this highway from this point to this point, how many vehicles are there. So that's density, right? So it's denoted by rho. So rho is a general notation. So you fix time, but you take the reading with respect to the distance. So that per unit distance can be per meter, per kilometer, or whatever it can be. Like here's an example. Here's the distance along road measured in miles, the number of cars they have measured, and then traffic density, they have computed number of cars per mile. So they want to define their rho as number of cars per mile. But the data they have collected is not of per mile, they have collected of per 1/4 of a mile. So from 1 to 1.25 there are 23 cars. From 1.25 to 1.5 mile there are 16 cars. From 1.5 to 1.75 miles there are 22 cars, and from 1.75 to 2 miles there are 8 cars. So within every quarter of a mile they have measured it, and then obviously to convert it to number of cars per mile they have to multiply it with 4. So that's the number. So that's the third column is depicting the traffic density. So it really depends upon what is your per unit distance, what is the unit of distance you are choosing. So accordingly you can do your calculation. So this is the observation. This is the data collection way, that how you are getting the data. So you sit at one place on the road and make the other person sit on other end of the road and start counting. So that's a conventional way of counting. That's the conventional way of taking the observations. So anyways, I'm not here telling you how to measure this, but what exactly it is, that's what I'm interested in. So I hope the meaning of density is clear. Next we are moving to another factor in the same variable density. So this data, if you look at on the left hand side table, density measured over extremely small intervals. So this is also per mile. Here also in the left hand side third column we are computing number of cars per unit mile, but the observation, like in the previous example, the observation was taken over every 1/4 of a mile, but here the observation you can see is 0 to 0.002, 0.002 to 0.004. So you can see the interval in which they are counting the vehicles is very small, right? Earlier it was 0, 0.25, 0.5, 0.75 and then 1. But here you can see it's like 0.002. So the interval, the measuring interval is very small. So you get this data, number of cars per mile, and then if you plot it, so you can see the plot on the right hand side. It's a discontinuous density function. So you can see from 0 to 0.002 there's no vehicle. From 0.002 to 0.004 there are 83 vehicles over here, and suddenly from 0.004 to 0.006 there are 333 vehicles. So there's a huge jump in the number of vehicles just on a moving on a small interval. So that's as a function of space, because On x-axis you are representing space. On y-axis you are measuring it, the density, rho. So rho as a function of x is highly discontinuous. It's 0, 83, 333, again 83, again 0, 0, 0, 0, again 333, 167 and 0. So it's highly discontinuous density function. So that's the problem which can occur if you choose your measuring interval very, very small. On the other side, if your measuring interval is very large, then you may get almost constant density. So the profile is bit not constant obviously, but it's more or less like a constant. It's not very much. It's a smooth function. It's not a discontinuous one. I've not shown the data, directly shown you the graph. But the problem with extremely large intervals is that the local variations in density are not captured. For example, if you just tell how many vehicles are there from, say, a road stretch of 30 kilometers. So you'll, over the whole highway, you'll just count the vehicles and tell this is the density or this is the number of vehicles. But they may not, that situation may not depict the real thing. The real situation can be that on a small section of the road there is a traffic jam. But since you were given the information, you are giving the information only about long stretch of road, you are not telling the tiny details occurring over the local parts of the road. So that's the limitation of taking extremely large measuring intervals, that the local variations in densities are not captured. So what we are trying to understand here, that if you take extremely small intervals, then there's a problem. And if you take extremely large measuring intervals, then also there is a problem. You may not depict an accurate representation of the real situation. So we'll talk about it then, what to do with it. Now we are moving about, now we are looking at the next variable, flow rate, which is also the fundamental variable. So in density, what was happening? The time was fixed, but you were taking the reading according to the space. So here we have fixed the space position. You can see the marking on the road is at a particular position A. It's just for depiction. So I'll be measuring the data by fixing my position, but the number of cars I'll be counting over time. So in density, you fix the time while count the vehicles over a distance, while in flow rate you fix the distance, you fix the position while you count the number of vehicles moving from that particular position per unit time. So that observation can be in half an hour, 15 minutes or whatever. So that's the flow rate if you read the definition. It's the number of cars passing through a particular position on road per unit time. It is denoted by Q. So like at the point A, I'm going to observe that what is happening. So again, if you take an example, so here is a table telling you the data. Like on left hand side, the first column tells you 7 to 7:30 a.m. So for every half an hour, the reading has been taken at a particular position. How many cars were passing through that particular position in these time intervals? And when you multiply, so these observations are taken over half an hour, but you want to see it over an hour, so you'll multiply with 2. So you'll get this number of cars passing per hour. So if you plot this, you will get this as your graph. So that's the flow rate. Now we are going to talk about continuum hypothesis. So you remember just now I told you that with the density, and same problem is with flow rate, that if you take your measuring interval too small, then also there's a problem. If you take your measuring interval too large, then also there's a problem. So the continuum hypothesis tells you that there should be a very precise measuring intervals. So in macroscopic traffic flow modeling, one is interested in the average behavior of the system as a whole, and number of vehicles is large. So we assume that such a measuring interval exists in both space and time. See, you need a measuring interval with respect to space in measurement of density, and you need a measuring interval for time in the measurement of flow rate. So we assume that a measuring interval exists in both space and time, in which both average density and average flow are smooth functions of space and time. Because I have just told you that both of these, flow rate and density, are functions of space and time. So we should be choosing our interval not too large so that it ignores the random or the local variations in density or flow rate, and we should not use our interval so small that the function turns out to be a discontinuous one. There should be like very much frequent jumps or oscillations in the data. So it should be something intermediate. So that's the meaning of continuum hypothesis. Such a measuring interval definitely exists in which the average density and flow are smooth functions. Smooth functions means they're differentiable. So you know what a smooth curves look like. It does not have sharp corners. It should not have discontinuities. So that's the assumption. So hypothesis. Hypothesis means this is true, and based upon this hypothesis we further derive the model and many other associated results with it. Okay, so that's about continuum hypothesis, which brings us out of that problem that what should be the interval chosen. And the third fundamental variable is speed. So obviously I'm not going to give you the definition of speed here. Everybody knows what is speed. So we know it's denoted by v, and v is also a function of space and time. So we have defined the three fundamental variables: flow rate, speed and density. The next thing is, because I want to derive a model, so I need to derive a relationship between these variables, that how these variables are connected. So right now I do not have any information about the system. I have just the definitions with me. So if you recall our very earlier lectures, so there I gave you a technique. The first technique of formulation of mathematical models was dimensional analysis. That we can use dimensional analysis to derive the relationship between variables. So we know the variables, so we can try the technique of dimensional analysis to get a relationship between them. So let's do that. So first variable is density. It is the number of vehicles per unit length or distance. So the dimension of rho is L minus 1. Flow rate is the number of vehicles per unit time. So the Q dimension is T minus 1, and the speed dimension all of us knows is LT minus 1. So we have three variables, rho, Q and V, and we have their dimensions with us. So I'm just writing it over here. So now we'll be using dimensional analysis to find the relationship between rho, Q and V. And for that I'm assuming rho raised to power A, Q raised to power B, V raised to power C is pi, which is a dimensionless constant. And now I'll substitute the value of rho, Q, V dimensions, and pi is M0, L0, T0. And you compare the equations on two sides, you will get A is C and B is minus C. The calculation is very easy. It gives you Q is rho V. So earlier you get Q dimension is rho dimension into V dimension, and then you imply that Q is directly proportional to rho into V. So but we know that from experiments that Q is exactly equal to rho into V. So because we know that the dimensional analysis has a limitation, it does not tell you the exact relationship, because a constant of proportionality can be here when you replace the sign of proportionality with equality. But from experimental data or from observations, we know that this is exactly equal. So here we are, we have derived the relationship between rho, Q and V, and we need to remember this for traffic flow. So flow rate is density into speed or velocity, you can say. So this is a fundamental relationship between the three variables of macroscopic traffic flow model. Q is rho V. So clearly if V is 0, then Q is 0. That means if there is no vehicle is moving, speed is 0. So obviously no flow rate. And if rho is 0, then also Q is 0. Means if there is no vehicle existing, the density is 0. So in that case also the flow rate is 0. So that's mathematically true also, and we are able to see that intuitively also. That makes sense. So this relationship is having a sense, and we have derived using this the dimensional analysis. We'll be using this further in the subsequent calculations related to macroscopic traffic flow models. So that part we are going to take in the next lecture. So in next lecture again we'll be focusing on, and we'll continue it from this point only. We'll look at what are the other details required for macroscopic traffic flow model, because right now we have not constructed the model. We have just defined the fundamental variables and derived a relationship between them, but that's not a model. That's a something which is going to be used in deriving the macroscopic traffic flow model.